Okay, good morning, everyone. So we're going to start a new unit today on feature selection, lasso, and maximum likelihood. So the demo for this unit has to do with prostate cancer. And there's something that you can measure in the blood called PSA, which is a commonly used indicator of prostate cancer. And there's a famous study that's used in a lot of machine learning classes where they had 97 patients that they were going to take out their prostates, and then they could measure various things about them, including PSA. And the way that this data set is usually used in machine learning classes is you try to predict PSA from the various things that they measured on these patients. And so this data set is actually used in the Elements of Statistical Learning book. And so that's where you can find it. It's in the Stanford website. And here is the list of the different features. Actually, one of them, the PSA or log PSA, we'll use as the target. And then the other things we'll use as features. And as I said before, there's a total of 97 samples in this data set. So let's start out by trying what we know, which is least squares linear regression. So in this case, we say that the targets are approximately equal to the predictions y hat, and the predictions take the form of beta 0 hat plus beta 1 hat x1, and so on, all the way to beta hat d xd. So again, in this example, y is the log PSA, and these x's are biometric features, and we have a total of d of them. So it's important to remember some of the advantages of linear regression, why we use it. The coefficients are very easy to fit. You can just run least squares very easily on this data set. And in particular, for this unit, the coefficients are easy to interpret. And what we mean by that is that the larger the jth coefficient, the larger the effect of the jth feature, right? Because if you find that you have various coefficients, one is much larger than the rest, and that means that that feature is being used much more to predict the targets. And we have to be a little careful with that. That only would be true if the features are roughly the same size. So like if one of these features was tiny, then you might need a very large beta just to counteract the fact that it's tiny. And so that very large beta might not be so important. It's just that it's trying to counteract the fact that the feature is tiny. So this statement about the larger beta, meaning xj is more important, this would hold true if the features are roughly the same size. And we're going to talk about that in just a few slides some more. Okay, so we do this. As we learned, we can just instantiate this linear model dot linear regression object, and then I don't know if we've seen this in the lecture yet, but last unit we talked about cross-validation, k-fold cross-validation, and we talked about a way of doing that with a for loop, actually two nested for loops. And there's a much easier way with scikit-learn. It's this cross-val score method. All you have to do is run this one command. So what you have to tell it is you have to tell it which predictor you're using. So we're going to give it this one we just created. You have to give it the training data. And you have to tell it what kind of cross-validation you want to use. So either you give it a number, like you could give it the number 5, and it would use 5-fold cross-validation. But one thing to note about that is if you just give it the number, when it does a cross-validation, it does not shuffle the samples. So it just takes like the first fifth of the samples, the second fifth, and so on. And that's pretty dangerous. If you don't know that your training samples have been shuffled, you have to be careful, or you have to give it a different cross-validation object. So here, in this particular demo, we're going to give it something called repeated k-fold cross-validation, which is like k-fold cross-validation, except you have it do this a repeated number of times, and every time you do it, you reshuffle the data. So that gives you a bit more randomness than if you just do it once with one shuffling. So that's what this repeated k-fold object is. And the last thing you have to tell cross-val score is you have to tell it what metric you want it to test in the cross-validation. And it always wants a score where larger is better. And so if you want to do something like RSS, or mean squared error, you actually have to tell it negative mean squared error, because larger negative mean squared error would be better. So this is the usual one you would use for RSS, or mean squared error. Anyway, so what it does is it gives you a list of the mean squared errors on each of the test folds. And then from that, you could just take the mean over those test folds, and we have to put in the negative to counteract this negative. And finally, you get the mean squared error from cross-validation, and this is for this least squares estimator. And we can print this out, and it turns out it's 0.4, which I guess we don't really know if that's good or bad, but the question, as always, is can we somehow do better? Okay, so that's where we get to feature selection. So what we learned in the last unit was that if you have too many features, then you get a large error variance. That's the bias variance trade-off, right? Too few features, you have a weak model, you get bias. Too many features, you have a very capable model, but a lot of variance. And the variance, we know it goes down as the training set grows, but in this training set, we only have 97 samples. That's not really very many. So what we would like to do is we probably want to reduce our variance. And one of the ways we can do that is we can use fewer features, because that's something also that we learned, is that the variance is proportional to d plus 1, where d is the number of features. So if we can reduce d, then we should have smaller variance. Of course, we're going to have higher bias, so we have to somehow balance this out. So if I want to use fewer features, the question is, which ones do I use? In the last unit, we just considered model order selection, where we always just remove the last one, like we would remove xd, and then we'd remove xd minus 1, and so on. And that might make sense for polynomial regression, but it doesn't really make sense for this data set, because there's nothing that tells us that the last feature is less important than the first. So really our question now is, which features do I want to ignore if I want to use fewer of them? Which are the most important ones? Which are the least important ones? And that is exactly the problem of feature selection that we're studying in this unit. We would like to use the best subset of D total features, but the whole question is, how do we figure out that subset? Okay. Any questions on the goal? So that's the goal of the unit. All right. So one approach we talked about briefly last time is what we would call exhaustive search. So we want to test every possible subset. Now remember that there are 2 to the power d of those when we have d features. So that is potentially a huge number. In this case, we only have 8 features, so it's doable. It's not a problem. We can test every one, and we can use that as sort of a baseline technique to see how that compares to all the other techniques we'll study. And remember, what we mean by testing every possible subset is you make that subset, and then you use k-fold cross-validation to compute an approximation of the test mean squared error. Fitting on the training data alone, that doesn't tell us anything. If we would look at training MSE, we would find that it's best to use all the features. So that's not interesting. We want to know how well our predictor will perform on some data we've never seen before. So for that, we want to use test mean squared error. And a robust way to do that is this k-fold cross-validation. Okay, so this exhaustive search, this is going to be the optimal approach. However, in practice, especially when D is large, you can't afford to do this. So for that reason, we're going to spend the rest of the unit discussing some other approaches to feature selection, such as stepwise selection, correlation-based methods, and regularization-based methods. And we'll spend most of our time on the last type, regularization-based methods. Okay, so first of all, what is this first method? Stepwise selection, or it's also called stepwise regression. So there's two different versions of this. There's forward selection and backwards elimination. So this is what we do in forward selection. We first find the single best feature. We do this by testing each feature one at a time to see how well it can predict the targets. And by testing it, we mean we evaluate the test mean squared error or approximate it using cross-validation. Okay, so we test out feature 1. How well does that work? Then feature 2 alone, how well does that work, and so on. So once we do this, we figure out what is the single best feature, the one that gives the lowest test RSS. So this is via k-fold cross-validation. Okay, so now that I have my single best feature, now I go through the remaining features and I find which is the second, which next feature do I want to add to my single best feature so that I get the best pair. And I do this by, I freeze that first feature, then I try, of all the remaining ones, the first, the second, the third, and so on. And again, I look at which one gives me the lowest test MSE. Oops. Okay. And then we repeat this process. So now we found our favorite two features. Now we go for the features that are still remaining, and we find which is the best of those to add to those first two features to get our favorite three features. And so on and so on. And eventually, so when you start doing this, you should see that the RSS, the test RSS will decrease. You know, you'll just use one feature, then with the second feature, it should do better. With the third feature, maybe it does better. At some point, it will start doing worse, because at that point, the variance is overwhelming the bias. So when it starts to do worse, you say, okay, I'm done. Let's back up and use the previous best features I found. Or sometimes you might say, I'm just going to stop at 5 features or 10 features or whatever. You will determine in advance how many maximum features you want. So that's kind of 2 stopping rules. Okay, so that's forward selection. Is that making sense? Process? Okay. Yeah.
What did the blue word say?
Via k-fold CV. Sorry about that. Okay, so that's forward selection. Now there's a very similar approach called backwards elimination, where you start by using all D features and you compute the test RSS again. And then you say, which single feature should I remove from that subset so that my test RSS is smallest? So you remove one feature, by testing out, removing the first, removing the second, and so on. And then once you figure out which feature to remove the first time, then you say, okay, I'm going to remove that forever. And now I'm going to figure out which is the second feature I want to remove. And so every time you do this, your subset decreases in size. And so the test RSS probably gets better at first because you're removing your variance. But eventually, once you have too few features, the bias starts overwhelming the mean squared error, and then the test RSS will start to increase. And so if that starts happening, then you go back and you say, I'm going to keep the subset which gave me the lowest test RSS. Okay, so those are 2 different approaches. Neither of them are optimal. They're what we call greedy or myopic. And the reason why is that they only look one step ahead. And as we know in life, if you make decisions using what seems best at the moment, you may not find in the long run you make the best decision. So that's what these do. They just look at which feature should I remove now, or which feature should I add now. That may not be the best in the long run, and that may not be the same set that exhaustive search would find. So these are suboptimal approaches. That said, they often work well, so they are commonly used. And backwards elimination is implemented in this routine sklearn RFVCV. So that means recursive feature elimination by cross-validation. Okay, so that's one approach. There's an example of this in the demo, though I don't have any snapshots in the slides. It's pretty straightforward to use. Any questions on this approach? Okay, so let's talk about the next approach. Next approach is totally different. So in this approach, what you do is, there's several variations of it, but one variation is based on cross-correlation. And the idea is the features that are most correlated with the target might be the best for prediction. So what you do is you measure the correlation with each feature in the target. So each time you do that, you get a single number, which is, you could measure like the normalized correlation, or this, here, the way I wrote it is you just measure this cross-correlation between y and xj. You do this for each j. And then now you get a list of correlations and you say, what's the single most correlated feature? What are the two best correlated features? What's the three best, and so on? And that will give you a sequence of subsets. And then you can use cross-validation to choose between those different subsets. Do I use just the single most correlated, the two most correlated, the three most correlated? You try them all with cross-validation, and you choose the one that gives you the lowest test RSS. Does that make sense? So that's all you do. So again, this is not going to be an optimal approach. And the reason why is that you could have two features that are both highly correlated with the target, but are almost the same, right? If, like, maybe two of the features are identical, so they would have equal correlation. But if you think about it, you would definitely not want to use both of them because they're totally redundant. You just want to use one. So it's not enough to consider something like cross-correlation with the target. And there are more sophisticated versions of this where they also add some penalty with the correlations among the features and so on. But in practice, I find that these don't work very well. They're definitely suboptimal. So now you could also replace correlation with some other metric, like, and they call these in general univariate statistics. By univariate, what that means is you're just comparing two variables, and you get one scalar statistic. And common examples of this would be mutual information, or f-value, or p-value. So these are just things that you are replacing cross-correlation with something else. That's the main idea. So the technique is the same, it's just you're using something besides cross-correlation. And these are all implemented in this command select k-best, and you just tell sklearn which is the metric that you want to use. And it's, again, pretty straightforward to use this. And if you don't know what mutual information or the other things are, don't worry. The point is you just try to come up with some statistic that measures something like correlation, and then use that. And none of them work super well, so. Okay, any questions? Okay. So the last approach, which I said we'll be spending most of our time on, is called regularization. And this is also suboptimal, but it works pretty well, and it also helps us learn some new concepts which are going to be really important as we move forward to other, future units in the course. Okay, so the way to understand this is that until now, when we did our machine learning, we always focused on a problem that looked like this. So we have some model and some cost. We'll just call the cost J. So this could be like RSS. And then our model coefficients are beta. And we said that our approach is just to minimize the cost or the loss with respect to our model coefficients. So now what we're saying is let's modify that a little bit. And instead of just simply minimizing this loss term, let's add one extra term here, which we're going to call regularization, or we can call it a penalty. And what this is trying to do is it's trying to tell us to be careful not to choose too many features. And so we would construct this last term so that the more features you choose, the larger the penalty gets. And as we'll see, there's different ways to do this. But overall, we're trying to say that just minimizing training RSS is not enough. So you want to add another term that causes a penalty so that you don't just keep adding more and more features. So this would be like, for example, training RSS. Okay, so again, the intuition is that the cost must decrease more than the penalty increases for you to want to use all those features. Okay, and in just a moment, we'll see two very popular regularization terms. Right. For now, is the main idea kind of clear? All right, so let's focus on, I think a better title would be regularized RSS. Okay, so we're going to focus on RSS. This is the old method. So we just minimize RSS, and this is our training data. And so what we'd like to do now is add a regularization term that allows us to still use our RSS but also do feature selection. So as we said before, the idea is to penalize the use of each feature. And by using a feature, we mean that beta j is not equal to 0. Because if beta j equals 0, that means I am not using xj at all in my prediction. Right? So that's going to be our goal. We're going to try to force some of the beta j's to be 0 so that we are not using the feature at all. Okay, and again, the intuition is we're going to add another term so that if you use the feature, the penalty goes up, and the RSS is going to have to decrease significantly in order to justify using that feature. So set beta j equals 0 unless the RSS is significantly reduced by a non-zero beta j hat. So we're going to, instead of minimizing just RSS, we'll minimize a cost j, where j is RSS plus phi, and this phi encourages the betas to be 0. So exactly how do we construct these phis? That's the next question. So there's two main ways to do this. So first there's L2 regularization. So here we have alpha times the sum going from j equals 1 to d. And then we have the absolute value of beta j squared. In L1, we have alpha, and then the same sum. We just have absolute value beta j. So if you want to visualize what's going on, we have this picture on the right, which compares these two things just looking at the jth coefficients. What we notice is, okay, here's our quadratic. This is our standard parabola. And then this absolute value penalty looks like this. The main thing to notice is that when you look at small values of beta, the absolute value is stronger than the square term, right? The red line is above the blue curve. So for small values of beta, the absolute value is a stronger penalty, but for large values of beta, the quadratic is a stronger penalty. So that gives a lot of intuition into how these two things will behave. When you add this kind of regularization, it will try to prevent any of the beta coefficients from being very large, whereas as we'll see with this one, it will focus on the small beta coefficients, and it turns out when you use this L1 regularization, it actually causes a subset of the betas to go exactly to 0. So we'll see that in just a second. The other thing in common is that both of these have another adjustable parameter called alpha, which determines the overall strength of the penalty. And the final thing to point out is that when we wrote these sums, we did not include the j equals 0 term. That's because we do not want to penalize the intercept term. The intercept term is just there to kind of counterbalance the sample mean of the y's and the sample means of the x's. That's all it's doing. So it's not something we want to penalize. It doesn't actually multiply any of our features. So we just want to leave that as is. Okay, so these are our two most commonly used options. There are many, many more, but these are the ones that most people tend to use. So before we go any further, we have to come back to this idea that all of this falls apart unless the features are about the same size. So when you look at these penalties, you notice that they are treating all the different beta j's the same. It's not like some beta j's get a larger penalty than others. So all the beta j's are being treated the same. But we said beforehand is that if some of the features are much larger than the others, then their corresponding beta j's might have to be very small to compensate. And if that's the case, then this uniform penalty may not actually work very well. So we want to avoid this issue. And we do this by normalizing the features. And by normalizing, what I mean is we set the sum of the squares for each feature, j. So the sum is done across the data samples. We set that to 1. So that, we're making the average squared value of the jth feature the same for all the different features j. Another way to see this is we know that this average square is the same as the sample mean squared plus the sample variance. Now there's one other thing that we tend to do. Remember how we don't want to penalize the intercept term? Well, we can easily do that by forcing the intercept term to 0. So if we remove the mean of both x and of the feature, all the features xj, then we learned in unit 1 and 2, we get the intercept term to go exactly to 0. And this is convenient now because it's 0, we can just penalize all the remaining all the remaining coefficients. So And also you can see here that if you remove the sample mean of xj, then this goes away, and then all that's left is the sample variance. So now we would want to set the sample variance to 1. So those are the two things you do in what we call standardization. So standardization, you set the sample mean to 0 and the sample variance to 1. And you want to do this to both the target and the features. So mathematically, you want to take your old features, and from each one of them, you subtract the sample mean of j, and then to what remains, you divide by the sample standard deviation, and then you just relabel that as xj again. So here is, these are your unnormalized ones, or unstandardized, and these are your standardized ones. So we do this also to our targets. Take the ith target, we remove the sample mean from it, we divide the result by sample standard deviation, and then we just label it as yi again. So this is what we want to do mathematically. The way that we do this in sklearn is we use something called the standard scalar. So first we instantiate this object, and then we use this command fit transform. It does two things. First, it does the fitting, which means it computes these quantities, and then it does the transformation, this, and these are our new standardized features. Then we do the same thing again to the targets, and we get our new standardized targets here. We have to do a little bit of NumPy gymnastics to avoid getting an error, because the fit transform wants to see a matrix. It wants to see something with 2 dimensions. So if you give it just a one-dimensional vector, it throws an error. So what we do here is we tell it, okay, think about this one-dimensional vector as a matrix with 1 column, and then we do a fit transform, and then we reshape it back to a one-dimensional vector. Okay, so this is standardization. It's a very important procedure. We could have been doing this all the way back since Unit 1, but it turns out that just for the least squares estimator, when you do the standardization, it doesn't change anything. What's important to us now is that we're doing regularization, and because of this regularization that we've added, let's see. Yeah, because of this term here, now it will have an effect. So that's why we're talking about it now. Any question on standardization? Okay. And there's one other important concept, and this especially is important in the project at the end of the term. So sometimes you have your training data, and then you have another test data or validation data fold. You want to make sure that the standardization you apply is exactly the same to both folds. So this is what I'm saying here. So standardize your test data using the training statistics, not the test statistics. So in other words, let's say I'm modifying the features. So I've computed my feature mean and standard deviations from my training data. Then I apply those to my training data, but I also use exactly the same statistics when I apply it to my test data. The reason we're doing this is because now exactly the same procedure, processing has been applied to train and test. That's one reason. Another reason is that you may not have enough test statistics to even compute these quantities. So for example, if I just have one test sample, then there's no way I can compute the standard deviation, and my mean estimate is also terrible, right? So that's why we always want to use the training statistics for standardization, not the test statistics. Okay, so in this particular demo, we don't have training data. Sorry, we don't have test data. So I don't have any code for this, but I just want to point this out. All right. Okay, so that's standardization. Any questions on that? Okay. All right, so now let's come back to combining our RSS with our regularization. And so we again have two ways to do this. We can use L2 or L1. And it turns out both of these give different names. So when you add L2 regularization to RSS, it's called ridge regression. On the other hand, when you combine L1 with RSS, it's called Lasso. And notice that as before, we're starting our summations at 1, not at 0. In fact, we're not even going to fit the beta vector at all. So again, this is standardized, right? So notice that because it's standardized, I am not using the A matrix here. I'm using the X matrix. The A matrix has that first column of 1s, and that's there as a way of fitting the beta 0 coefficient. But now the beta 0 coefficient is not even here. There's no beta 0. Because we know it equals 0, so we're not even fitting it. Let me show you one other thing. When we instantiated the estimator way back over here we go, we told it fit intercept equals false. So we're telling sklearn do not fit the beta coefficient. Because we standardize our data, we know it should equal 0, so let's not try to fit it. Okay. So as a result, we can write our model with y minus x times b norm squared. So we saw this norm is just the standard Euclidean norm, sum of the squares squared. And now this is also the standard Euclidean norm squared. We're taking the norm of beta. Okay, so whenever you see these double bars without any subscript here, that means you assume the usual norm. And if we're talking about vectors, the usual norm is the L2 norm or the Euclidean norm. Now, when we go to the next example with L1 regularization, the first term is identical to before. The second term is missing the square there. So note that there's no square, and as a result, we give this a different notation. This is called the L1 norm, which is just the sum of the absolute values. So we're denoting that with this little subscript 1. So all norms are ways of measuring distances between points or measuring the lengths of a vector. So let's get some intuition about what's happening here. Imagine that I have 2 points. I'll put one at the origin, and I'll put another point here. So if I ask you how far are those points away or how long is the vector containing them, you might be tempted to say, this is the length. And that would be correct if you're talking about the Euclidean norm or distance in the L2 sense. But if you are a taxi driver in Manhattan and you can only drive the city streets, you can't go like a bird flies, then you might say that the distance between those 2 points is actually the sum of from here to here and then from here to here. So this would be the L1 distance. Okay, so it's just another way of measuring distance. And that's why they're both norms. Okay, any questions on Lasso or ridge? Okay, so let's study them a little bit more. Let's focus on ridge first. Okay, so here's the ridge cost. RSS plus alpha times the sum of the squares, which we know is L2 norm on y minus x beta plus alpha times L2 norm on beta itself. And we can use a very similar derivation to what we did back in Unit 2 to derive the minimizer of this, the beta that minimizes that. And it turns out it has this expression here. And as you can see, what's different than in the standard least squares is that we have this term now. So for example, if I set alpha to 0, then I'm back to standard least squares. I would get rid of this and I'm back to standard least squares, right? But now I have this term which gives me this here. And one interesting thing is that even if this matrix is non-invertible, once you add this scaled identity with alpha greater than 0, now this thing will be invertible no matter what. So for example, if you used your one-hot coding and it was redundant, it wouldn't matter. At this point, this would allow you to do the inverse. Okay, so this is the ridge regression. So the question is now, why, in what cases would we be motivated to add this penalty? And it turns out the main motivation is when the columns of X are highly correlated. It turns out that when this is the case, and let me give you just sort of a visualization. So if you have data, see this picture might not be so great, but if you have data that is highly correlated, then the squared loss has contours that look like this. They start to get very, very stretched out. And in fact, if they get perfectly correlated, which happens when this becomes singular, then you have just a perfect line here, and all the points on the line are equally good at minimizing RSS. But that doesn't mean that you want to use them all, because if you choose a point on the line that's very far from the origin, when you use that for for predicting a test sample, the fact that this has such a huge norm means you can get a really crazy answer. So again, when you do this with highly correlated X, you can get, the solutions you can get can have very large values. And the result is that your test prediction will be very sensitive to test data. Is another way of saying overfitting. So what people tend to do is that they penalize the norm of beta squared, which, as you can see, directly discourages large betas. In the lab of this unit, you will have an example where this matrix X is very wide. It has thousands of columns and only like a few hundred rows. And as a result, this is extremely singular. It has many, many eigenvalues equal to 0. And you definitely need to do this even to invert it, but you'll see that by making alpha appropriate, you can get a huge benefit in terms of your test RSS. So this is the main reason that people use ridge regression. It turns out that it does not cause any of the beta coefficients to go exactly to 0, and therefore it does not perform feature selection, which is one of our main goals in this unit. So it's not really useful for feature selection, but it is useful for correlated columns. Yeah?
choice of alpha, is that from the data, or is that, can we derive from data, or is it like a hyperparameter?
It is a hyperparameter, and as we'll discuss, it's something that we want to tune using cross-validation. So we make a grid of many possible alphas, and then we test each of them with like k-fold cross-validation until we find the best one. Okay, this is a good question. Okay, any other questions? All right. So here's another way to visualize what happens as you change the regularization strength alpha. So this thing is called the coefficient path, and it's plotting beta j, actually all the beta j's versus regularization strength alpha. So here's alpha on the horizontal, beta's on the vertical, and you can see that as alpha goes to infinity, as it gets larger and larger, you care less and less about fitting this term, and you care more and more about making this small, right? So eventually, as alpha goes to infinity, it just forgets this completely and sets all the betas to 0. And that's what happens as you go in this direction. So here we have like, this is on a log scale, so this is 10,000. Now, if you go all the way to the left, and alpha gets tiny as it approaches 0, you just have least squares. So these are your least squares coefficients, and then it transitions smoothly to them all being 0. And of course, the interesting stuff is in the middle. So when we do this cross-validation, it turns out that we'll find that this alpha is optimal, and that's what the dashed line is there to indicate. But again, you see in this picture, you don't see any of the coefficients going exactly to 0 until you get to alpha equals infinity, so it's not doing feature selection. Okay, so I think that's it for ridge regression. Are there any questions? Ridge, all right. Let's do lasso next. It's very similar in spirit. Remember that the only difference is we're changing the norm here. So we have a L1 norm. But as a result of that, there are several differences. So the first difference is that there's no closed form expression for beta. This is something you have to solve using an optimization algorithm. Now, fortunately, this optimization problem is what we call convex. We'll talk in detail about that in Unit 6. But for convex problems, there are solvers that are guaranteed to find you a solution. So as long as you can do the optimization with an off-the-shelf solver, it's not a problem. You'll get there eventually, but you can't write down the expression. Okay. And for this particular problem, there's been a lot of different solvers that have been derived and proposed, and a few of the famous names are Vista or ADMM, GLMNet, and so on. And not surprisingly, sklearn has a lasso method that does all the solving for you, so you don't have to worry about it. So it's very straightforward to do. Although computationally, as your data set gets larger, it is more expensive. It takes more time to compute the solution, much more time than Ridge. Okay, so what do we get from this additional computation? Well, as we'll see, it leads to exactly zero-valued coefficients, and thus it performs feature selection. It tells us exactly which features it thinks we should not use. And as we'll see, the number of non-zero features is controlled by alpha. If you look at this cost, you can see the larger alpha gets, the more you care about setting the absolute value to 0. So larger alpha means more of these betas will be exactly 0. But there's another problem with that. When you set a few of them to 0, you are placing a penalty on the remaining betas. And that penalty is usually not something we like. It actually is biasing all our coefficients to 0. So this is one of the challenges with Lasso. The non-zero beta j's become biased towards 0. And so for this reason, we don't actually want to use them for prediction. So we ignore them, and we keep only the indices that Lasso tells us to keep. It just tells us, if it says keep coefficients 1, 6, and 8, and here are their values, we ignore the values it gives us. We just remember 1, 6, 8. Okay, I'm going to keep those. I'm going to do regular least squares linear regression with those. That's it. Okay. So let's look at its coefficient path to it's very insightful. So here again, we're plotting versus alpha. These are the coefficient values. And if you go far to the left, where that L1 penalty is not really active, you'll have least squares coefficients. As you increase alpha greater and greater, eventually you'll get to the point where all your coefficients are exactly 0. So this is not going to be very useful, right? So what's interesting is the region in between. And as you gradually increase alpha, you can see here, this brown line, this is the first feature that turned off. It turned off exactly there, and after that point, it stayed off. If you increase alpha a little bit more, then this pink feature turned off. A little bit more, the green one turned off. A little bit more, the red one, and so on. And so cross-validation suggested to us that we should set alpha this way, at which point we are keeping 3 non-zero features and all the other ones are at 0. So what we would then do is we'd notice, okay, if these are the 3 features we should keep, then let's do least squares linear regression with those 3 features. So again, just to summarize, the main 2 things we see in this coefficient path is larger alpha leads to, number 1, fewer non-zero features, but also smaller amplitudes. And this is, I'm going to make a little frowny face there because this is not something we like. We don't like the fact that this blue coefficient has decreased from here to here, and then these, that is an unfortunate side effect of the bias. Okay, so any questions on the Lasso coefficient path? Or okay, so one of the advantages of linear regression that we mentioned earlier is that it can help us determine in a scientific experiment which of the features are most important and which ones we should ignore. So if we are medical researchers and we're trying to understand, which things are most predictive of PSA levels, then this data set would tell us we really should be only looking at these things, LCA vol, L weight, and this Gleason score. Everything else we should just ignore. These are the features that are most useful. So that's one of the advantages of linear regression. And once you start to do something nonlinear, like a neural network, even though the answers may be, like the prediction may be better, it's very difficult to understand what the model is doing, and it doesn't tell you directly which features are the most useful. So this linear regression, even though it's a simple model, it has certain advantages for feature selection. Okay. So as before, we could try to choose alpha via cross-validation. Although I'll have more to say about this, we have to think pretty carefully about exactly how we should be doing that. So let's just summarize these 2 methods now that we've covered them. So Lasso is RSS plus an L1 penalty, whereas ridge regression is RSS plus an L2 penalty. Lasso tends to produce many exactly zero valued beta j, which means it's great for feature selection, but a disadvantage is that there's no closed form solution. We have to solve it numerically. On the other hand, ridge regression has an advantage. The solution can be written in closed form. It tends to produce many small beta j, but none of them exactly zero, and so it's not useful for feature selection. But if you have highly correlated features, you might find that it's a very good tool. A little bit of the intuition about why Lasso gives you exactly zeros and L2 does not. It's given in these pictures. So here is your RSS. Here is your L1, or here is your RSS, and here's your L2. And you have to do a little bit of mental gymnastics. The cost function is actually the sum of these two. So kind of imagine adding those two contours together and looking for, again, trying to find, this is going to be like your beta 2, your beta 1. What is the beta 1 and beta 2 that's going to minimize the sum of those two? Because of the pointiness of this, it tends, the minimum tend to happen along the coordinate axes. And here you can see the minimum happened right there. And that is why we're getting what we call a sparse solution. It's a solution where beta 1 is non-zero, but beta 2 is 0. So that's why it's setting this beta exactly equal to 0. On the other hand, down below, because this is doesn't have these pointy edges, its solution will be over here. And you can see this is non-sparse. It's going to have non-zero beta 2 and beta 1. Okay, a little bit of the geometric intuition about why Lasso gives you exactly zeros. So, so that's all we have time for today. So next time we'll talk about how to implement this, and we'll get into some details about exactly how we want to do that cross-validation tuning. All right, see you guys on Wednesday.